Have you ever found yourself standing next to a really massive piece of heavy machinery, like a giant mining truck or a heavy-duty industrial tractor, and you just feel that immense wave of heat radiating right off the engine? It kind of makes you wonder, how do these colossal, high-power vehicles keep from completely overheating and literally melting down under such intense, nonstop workloads? Well, today on The Explainer, we're going on a really fascinating journey to answer exactly that. We're going to start by looking at these macroscopic, giant machines, and then we're going to zoom all the way down into the microscopic world of fluid dynamics to find out how they actually stay cool.
Welcome to The Explainer! I am so thrilled you're here with us. Today, we're decoding the mechanical heart of high-power cooling systems, a component known as the hydroviscous clutch, or HVC. And specifically, we're going to explore a groundbreaking new mathematical approach called the DMAR model and discover how it's totally changing the way these clutches are designed and understood.
Okay, let's dive into this. Here is our roadmap for today's zoom-in, zoom-out journey. We'll start with high-power vehicle fan systems, go inside the hydroviscous clutch, and tackle the oil groove problem. Then, we'll introduce the new DMAR model, break down the 3 stages of friction, and finally wrap up with optimizing speed regulation.
Starting things off with Section 1, high-power vehicle fan systems, the cooling powerhouse.
Before we get into the microscopic details, let's look at the big picture of how massive engines stay cool. Heavy vehicles rely on gigantic cooling fans, right? But you absolutely do not want that fan running at full blast all the time. That wastes precious energy, it creates massive noise, and it just causes unnecessary wear and tear. Instead, these vehicles rely on this amazing concept called stepless speed regulation. Basically, this means the fan smoothly and seamlessly adjusts its speed on the fly to perfectly match the engine's real-time cooling needs. There are no clunky gears shifting, no sudden jerks. This incredibly smooth regulation is absolutely crucial for the overall stability, efficiency, and safety of the vehicle while it's operating.
Moving right along to Section 2, inside the hydroviscous clutch, the mechanical heart.
Now, what's really interesting about this mechanism is how elegantly simple it actually is. In an axial motion model of the clutch, you've got separated plates being driven by the engine on one side. On the other side, you have friction plates connected to the cooling fan. But here's the kicker, they aren't actually touching right away. In between them is a microscopic gap filled with an extremely thin film of lubricating oil. The engine's rotational torque is transmitted right across this gap purely through the shear action of that fluid. By subtly pushing the plates closer together or pulling them apart, the system changes the oil film's thickness. And that tiny change smoothly alters how much torque gets transferred, which in turn seamlessly varies the fan's speed. It is fluid power at its absolute finest.
Which brings us to Section 3, the oil groove problem, and the major flaws in the old math. So, here's where things get a bit messy. The old calculation models, they were basically cutting a massive corner. They used a single fixed contact area ratio coefficient to figure out how much torque the clutch can handle. Essentially, they treated the whole plate as if the fluid and the friction behaved the exact same way everywhere. But reality is so much more chaotic than that. As the clutch spins at extremely high speeds, the immense centrifugal forces create a gyroscopic effect, causing the oil film to physically shrink and actually pull away from the outer edges of the plates. On top of that, the surface area literally changes due to the groove patterns as you move radially outward from the center. A fixed, static number simply cannot account for these complex, real-world fluid dynamics.
Engineers actually carve incredibly intricate, tiny grooves right into the metal friction plates to help the cooling oil flow through the system and prevent overheating. But the patterns are wild, they're complex and highly varied from plate to plate. If you try to apply a generic one-size-fits-all mathematical model to these entirely distinct topographies, your calculations for load-bearing capacity and torque are going to be fundamentally inaccurate. And let's be honest, when you're dealing with multi-ton industrial machines, inaccurate is a quick recipe for system failure or, at the very least, terrible operating inefficiency.
Enter Section 4, the new DMAR model, our mathematical hero.
This is where the DMAR model comes in. That stands for Discrete Micro-Ring Area Ratio. And conceptually, it is brilliant. Instead of treating the friction plate like one big uniform disk with a fixed ratio, DMR mathematically slices the friction plate into incredibly thin, concentric micro-rings. By using this integration method, engineers can calculate the fluid load-bearing capacity and the exact surface area ratio for each specific microscopic ring as they move outward radially. It's essentially like upgrading from an old, blurry pixelated photo to a crisp 4K resolution image.
It gives us a highly accurate map of the forces without getting completely bogged down in simulating the intensely dense standard fluid dynamics equations for the entire system. Ultimately, this new math paves the way for us to design truly optimized plates.
Let's look at how this plays out in Section 5, 3 stages of friction, the physical journey.
And this brilliantly illustrates exactly what happens when that clutch engages. It goes through 3 really distinct working states. Stage 1 is fluid lubrication. The plates are completely separated by oil, functioning a lot like a car tire fully hydroplaning over a wet road. Pure fluid transmission. Stage 2 is mixed friction. The plates are squeezing together, they're still slipping against each other, but they are just starting to physically grab. Finally, we hit Stage 3, boundary friction. The oil is mostly squeezed out, the plates are locked firmly together, and they rotate together as one single solid unit.
During that critical transition in the middle, the mixed friction phase, things get really interesting. At a microscopic level, these metal plates, well, actually, scratch that. They aren't perfectly smooth at all. They have this rough, jagged microtopography. During mixed friction, the mechanical load isn't just floating on the oil anymore. The physical, solid bumps on the plates begin to literally crash into each other and share the immense load with the remaining pockets of oil. The DMR model is remarkable because it's the first to really accurately map how these tiny microbumps and the fluid interact dynamically as the clutch engages. Finally, zooming back out for Section 6, optimizing speed regulation, the big picture.
Using the DMR method, the researchers didn't just solve some tiny, isolated math puzzle here. They took this logic and built a staggering 32 degrees of freedom's dynamic model for the entire fan drive system. 32 degrees of freedom. That represents an unbelievable amount of computational power, tracking dozens of moving variables all at the same time to predict the dynamic responses of the entire vehicle cooling system with a level of precision that was basically impossible before.
Let's move along and see how this builds into real-world results, because the data from their physical experiments was just phenomenal. The DMAR model accurately predicted the exact axial engagement force required. It perfectly matched the experimental speed regulation curves, meaning the math mirrored physical reality almost flawlessly. They even uncovered a hidden oscillation, a tiny mechanical jitter at the steady-state boundary that the old math models completely missed. Most importantly, this massive success lays the foundation for engineering fully optimized friction plates for heavy machinery moving forward.
Which brings us to a seriously exciting frontier. Think about it. We've just seen how solving a microscopic math problem about the area of a spinning disk can completely revolutionize the stability and efficiency of a giant, macroscopic industrial machine. It's crazy how interconnected the microscopic and macroscopic worlds really are. So it leaves us with this final thought to ponder. With the DMAR model finally unlocking the complex microscopic secrets of fluid dynamics and friction, what other stepless mechanical systems around the world are sitting out there right now just waiting for a massive upgrade?